welcome to another lesson. Today we're going to be going over AP Calculus AB Lesson 5 Continuity. So we're going to be describing the basic concept of continuity, and we're going to learn how to apply it with our limit functions. So, a function is defined as continuous if it has no holes or breaks. What does that mean? If I have a function f of x, okay, cross these out for later. If I have a function f of x on the xy plane, and it looks something like this, is that function going to be continuous? No, because there's a hole and more or less a break because the hole is a break. But what if I had something like this? Something like this, the dot there, and the dot there. Is that continuous? No, because not every single y value is being fulfilled. There's no y value that exists here. So in order for a function to be continuous, there has to be basically a y value at every point, and they can't really have any holes or breaks. So that's the basic idea of a limit. Now let's go into the three exact conditions of continuity that you're going to need to know for your AP Calculus exam. So, our first condition of continuity states that f of c is defined, which means if you have a function f of x and you plug in a constant c, when we plug in c, we have to get a y value always. This has to equal something, which means for any value of x that I plug into my equation, I'm going to get a y value of some sort. Any value of x. So it means if I can go to infinity, there's always going to be a y value to answer my prompt, right? So that's basically the first condition of continuity. Now, the second condition is a little more complex, and it states that the limit as x goes to c, a constant, of f of x exists. There just has to be some sort of limit, which means if I have a function plotted, and I take any random point, any constant on the graph, let's pick here, there has to be a two-sided limit. Notice how it doesn't say from the left or from the right. It just says it approaches the constant from both sides. So we have to have a two-sided limit on our function. So if I circle here, boom, we got something approaching on that side, approaching equally on that side at the same y value, which means the double-sided limit exists. So that's what it's just saying here. It's saying that there's a double-sided limit at any constant c. Now for a third condition of continuity, it's saying the limit actually equals the value that you're plugging in for the limit. So if I have the limit of a constant c, right, of a function, sorry, as it approaches a constant c, it's going to equal as if I plugged in f of c. So we know in our very first ideas of limits with computing limits, we would just plug this in here and we would get f of c, right? So it's saying for the function to be continuous, this has to be true. So if I say limit x goes to 2 of f of x, this better equal f of 2, right? Which means basically if I have a graph and then let's say something like this, right? And there's a hole there, but it's filled in there, right? Technically it's continuous based on the first two functions of continuity. However, based on our third rule of continuity, sorry, not functions, it's not continuous because even though it fulfills a y value at every single point, the y value is not equal to the same x value that you plugged into the function, which makes it not continuous. So we're going to be going over a few examples where we go through our rules to see if the function is continuous, and we're going to make a checklist. It's in sequential order, so something may fulfill the first, may fulfill the second, may fulfill the third, and then it's continuous. But if it just fulfills the first and second, and it doesn't fit, if it passes the first and second, but it doesn't pass the third, it's not continuous. Same thing with the first. If it doesn't pass all three, it's not continuous. But you may be wondering, can I pass one, fail two, but pass three? No, it's sequential. Okay. So let's do some examples, right? Let's start off with some graphs that'll give you. So if I have a graph like this, and I plot a function f of x, and it looks something like this, with the whole at x equals 3. Which condition does this fail? I'll give you a moment to think about it. You can pause the video and try to figure it out yourself. Okay, so it fails condition 1. This is where condition 1 is already failed, because if we go back up here, f of c is defined. There's a point right here. F of 3 is not defined anywhere on this graph, so therefore the first condition is failed by this. However, let's move on to another example. If I have a function that looks like this, filled in point there, a hole right above it, and it continues on in the xy plane, which condition does this fail? Well, let's run through number 1. Does it fail number 1? Let's see. Does f of c exist? Yeah, f of c exists. It does exist, so condition 1 is true, right? It passes condition 1, so I'll put this in green here. Passes condition 1. Put that in green. Put what it passes. So it passes condition 1. Good. Does it pass condition 2? Well, what does condition 2 say? It says, as I approach the constant, it is the same y value. So does the double-sided limit exist here? It does not exist. So therefore, number 2 is failed. So it's not continuous. Alright, let's move on to a third example. If I have a function f of x that looks like this, I have a hole, and then right above it is a filled in point. Let's run through our first rule. So our first rule, continuity, states that f of c exists, does it? Yes. If I plug in, let's say this is 3, I'm going to get a y value, let's say 2. There's a y value for this point. So yes, condition 1 is passed. Condition 2, does the double-sided limit exist? It definitely does. The limit approaches here at the same y value. Okay, condition 2 is passed. What about condition 3? It states that if I plug in 3, I better be getting an f of 3 as my limit. Oh, and I most certainly am not. Well, I am getting it as my limit, but I'm not getting it as my answer to my limit. So I'm not going to get the same y value fulfilled as the limit points to. So let's say this is 1. This should be filled in as a 1, but it's not. I'm going to get a 2. So if I have the limit as x approaches 3, right, of this function f of x, this is not going to equal 1 like I want it to. It's not going to equal f of 1. It's going to equal, it's not going to equal f of 3. It's going to equal f of it's going to equal 2, and it should equal 1, because f of 3 should be 1, but it's not. It's up here too, and it's not continuous. Okay, that might have been a little vague there, so let's move on to a few more examples algebraically. Okay, let's do one algebraic equation, and then I'll leave you guys to go ahead and study this on your own, do your homework. So if I have this piecewise function, h of x, and it equals x squared minus 4, rational, x minus 2, when x does not equal 2, and then it equals 4 when x equals 2. Is this continuous? Yes or no? Now this is a trick question. Yes, it is continuous. You're probably thinking that it wouldn't be. Why? Let's run through our conditions of continuity. Condition 1. There has to be a y value for every x value. Is there? Well, when x doesn't equal 2, there's y values. And when x equals 2, there's a y value. So therefore, condition 1 is passed. Condition 2. The double-sided limit exists. If I approach 2 from both sides, I'm going to get, if I approach 2 from the left, it's not going to equal 2, so therefore I have to plug in here. What's 2 equal to? I'm going to have to plug in 2 to this composite sort of thing. So let's plug in 2. And we're going to get 2 squared minus 4 over 2 minus 2. That's an indeterminate form, right? It's going to be over 0. It's going to be 0 over 0. So how are we going to fix this? Let's do a quick factoring here. And we're going to have x minus 2 times x plus 2 over x minus 2. Cancel these. And if we plug in a 2, what are we going to get? 4. So therefore the limit is the same as the x value that we're plugging in. And we just answered both condition 2 and condition 3 in the same one because we had the double-sided limit. And the double-sided limit is the same. If this were, let's say, to equal 5, condition 3 would not be met, right? And this would not be continuous. But since the limit is, the y value of the limit is the same as the actual y value of the function, it's continuous. So I hope you guys enjoyed the video. I hope it made a lot of sense. I hope you learned a lot. Thanks for watching. Make sure to like, subscribe, and follow me on my journey. Thank you.